So we need to estimate the area under the graph of y equal x squared. Where x goes from 0 to 1, okay, on the closed interval 0 to 1. So this is the task, and let's move to the next page to visualize it. Okay. So at this point, we're not talking about distance and velocity and so on, just straight out find the area. So let's sketch this function. And of course, we're looking at the right side of the parabola y equal x squared. And when x equals 1, y equals 1 as well. So we have one endpoint at 0, 0, and the other at 1, 1. And in between, we have the right side of the base parabola y equal x squared. And what we're interested to find is the area below the graph, or between the graph and the x-axis when x goes from 0 to 1. Okay, so this area. Now, I don't have a clear geometric shape here, figure, that allows me to calculate. So I can do the initial rough estimate. For instance, instead of calculating the area under the curve, I can calculate the area under the hypotenuse of a right triangle, like so. Now I know that this is rough estimate, and I'll call it. I'll say that a rough estimate is the area of the right triangle. Okay, so we're going to say that A is approximated. And what is the area of this triangle? Well, it will be 1/2 base times the height, but both base and height equals 1. So it will be 1/2. Okay, now obviously this is an overestimate. Why? Because we have all this extra area right here between the secant, which is in this case, and the curve. So this is an obvious overestimate. So at this point we can conclude. So we know that A has to be less than 1/2. That's the best information we get from here. So we need to think about better ways to estimate the area. And if you think long and hard or short and hard, depends how quick you get to a conclusion. One conclusion is, how about if we'll divide the interval from 0 to 1, let's say into 2 or 4 or 8 or 10 pieces. Okay? So we can say that a better estimate is obtained by dividing the interval 0 to 1, let's say we'll choose into 4 equal intervals. So let's visualize it again. Let's sketch a graph that demonstrates it. I can draw it here, but I think it will be too cluttered and it will be harder to follow the technique. So it's better to redraw or resketch. So we go 0 to 1, and we have 1, 1 right here. So what we are saying is the following. We're going to break it into 4 equal intervals. So this will be 1/2 in the middle, 1/4, and 3/4, like so. And now I'm going to slice this area into 4 pieces, equally spaced. Okay. Now I need to estimate each. So the first thing I'll do, I'm going to build up blocks, rectangles, in the following fashion. I'm going to say the y value of the first interval from 0 to 4 will be what we have on the right endpoint. Remember, this is the function y equal x squared. So y will be the square of x. So the value here will be 1/4 squared. Okay? And then the next block will be built on the right endpoint value of y, of the interval. And this is at 1/2, so the right endpoint values will be 1/2 squared. The next block, or next rectangle, will be built based on the right endpoint value of the third interval. And this will be f of 3/4, or 3/4 squared. And lastly, the fourth quadrant rectangle will be simply 1 squared, or 1. Okay? Now, since we're assigning a y value for each interval at the right endpoint, this is what we call a right endpoint. So let's see, we're going to estimate the area of the first block, and the first block is this one, will be the width is 1/4 and the height is 1/4 squared. Right? This is the area of the first rectangle. The second rectangle, the width will be 1/4, but the height will be 1/2 squared. The third rectangle is 1/4 times the y value is x squared, x equals 3/4, so we are looking at 3/4 squared. And finally 1/4, and the y value is 1, so we have 1 squared, which is 1. Okay? Now, what happened is, this is what we call a right endpoint sum, because we add the values of the right endpoints of each interval. So this is a right endpoint sum, and we have even notation, and we call it, it's equal R sub 4. Now R is the right endpoint sum, and of course 4 is the number of intervals. Therefore, the notation will be R4 or R sub 4. In this case, if we add these together, we have a common factor, which is 1/4, the width of each interval. Okay? And then we add the values of what we have inside, and we have 1/4 squared, which is 1/16, and then 1/2 squared, which is 1/4, and then 3/4 squared, which is 9/16, and then we have 1. And of course, the common denominator would be 16, so it will be 1/4 times 1 plus 1/4 is 4/16, 9/16, and then 1 is 16/16. Add this up, and you get 1/4, and let's see, 16 and 9, 25, and 5 is 30. So it's 30/16, or 6 anyway, we can write it as 30/64, or 15/32. And notice that 15/32 is less than 1/2 that we had before. So this is a slightly better interval, a slightly better estimate. It's still an overestimate. Why? Because we have all these pieces above the curve, right? The portion of the rectangle is not above the curve. So we're going to say that, note here, R4 is still an overestimate. It is less than half, so it's better than the triangle. So what we're going to do next